All right, after taking our little break to understand that adjoint notation a little bit further, we're ready to move on with some more definitions and examples. So the next thing I'd like to present is the definition of a subring. So suppose that you start with a ring R and you're looking at a subset of that ring that happens to be a ring and happens to be a ring under the exact same operations as R. Then we say that that subset S is a subring of R. So let's clarify this definition a little bit with some examples. The first example, and a rather nice example, is a set of even integers. So here the set of even integers is our subset S. Our original ring R is the set of integers. And it happens to be the case that the even integers form a ring. And you could take this a little bit further. It's not particularly important that we have the even integers. Right? Even integers are just numbers that are a multiple of 2. If we looked at multiples of 3 or multiples of 57, so we looked at things of the form nz for any particular integer n, we would also have a subring of the integers. The reason that something like the even integers or things like nz are good examples to consider is because the even integers don't contain the number 1 as part of that subset. The number 1 is an odd number. As the number 1 is not divisible by any number n, this would work for nz as well. But this is a way to get an example of a commutative ring that does not have a unity. And if you looked back on our previous slides in the first video on the introduction to rings, all the examples of rings we gave happen to have a unity. So you can take the even integers as an example of a ring that does not contain a unity element. Another thing I'd like to point out, this isn't actually an example, it's a non-example, but those are also helpful for clarifying your understanding. Z mod n is not actually a subring of the integers. It is true that if you were looking at the collection of integers, the numbers 0 through n minus 1 is a subset of the integers, and you do have operations, that set does happen to form a ring. The problem is that it forms a ring under different operations than that of the integers. The operation for the integers are addition and multiplication. The operation on z mod nz is modular arithmetic or modular addition and modular multiplication, and those are technically different operations than just addition and multiplication. So z mod n does not form a subring of z. This is an easy confusion to make. And if you initially had this suspicion about z mod n, I would still think that you had some good thoughts going on and that you were thinking about things properly. There is a relationship between z mod n and z. However, the relationship is not properly categorized as a subring, but we will explore this relationship as we get further on in the semester. Another thing that is a real and actual example is if we take GLN of f and SLN of f. These happen to form subrings of MN of f, where if you'll remember or you'll look up in Gaussian, GLN of f means the general linear group of n by n matrices with entries in f, and SLN of f means the special linear group of n by n matrices with entries in f. Remembering where f can be something, it can change back and forth between perhaps the integers mod n, rational numbers, real numbers, complex numbers. Now, if we wanted to check that a particular subset of a ring happened to be a subring, one way that we could go about doing this is we could prove first and foremost that S forms a ring. And the next thing we could note is that it happens to form a ring under the exact same operations. However, if we are going to check directly from the definition that we gave of what a ring is, we're going to have to check a lot of properties. So we would have to check that the set S forms an abelian group under addition, and that contains 5 properties within it, the 4 group properties that we would need to check, and then we would also have to check commutativity of the addition operation. And then we would have to check the remaining things that were baked into the definition of ring. So we would have to check that there's a multiplication structure on S and that S is closed under that multiplication. we'd also have to check that that multiplication was associative, and we would have to check the two different versions of the distributive property. And so if you start taking a list and counting, depending on how you're counting, that's probably something like 8 or 9 requirements that or things that you're going to need to check about the set S, and that would be ridiculously tedious. So luckily for us, there's a really nice theorem that says you don't need to check all of those things. It's sufficient to check 3 things. So here's what we've got to check. Suppose that we start with a subset S of a ring R, and we want to know if S is a subring. Then it's enough to just check these 3 properties. The first thing we can check is that S is non-empty. Typically, although I won't say always, just as it is in group theory, typically it's easiest to check that the additive identity belongs to S, to check that it's non-empty. The next thing that you want to check is that the set S is closed under subtraction. That is, if you take elements A and B, and you assume that they belong to the set S, you would want to show that A plus the additive inverse of B also belongs to the set S. And then the last thing that you need to check is that S is closed under multiplication. So what this would amount to is you pick 2 elements, A and B, that happen to belong to S, assume that both of them belong to S, and show that their product also belongs to S. Now, in this slide, since this is mostly meant to be review, we're not going to actually prove this theorem right now in this video. However, I do think the proof is sketched a little bit in your textbook, but the idea of the proof is really similar to the proof of the 2-step subgroup test, so I feel a little bit less guilty because I know when I taught abstract I did the proof of the 2-step subgroup test. And just as a sketch of what the proof is, or what the main idea is behind the proof of this theorem, is you show that all those other properties that I sort of listed at the beginning of this slide verbally happen to be satisfied as long as these 3 things are satisfied. Now, as an exercise, what I do think would be a good use of your time is maybe less so than a better use of your time than going back and really reviewing the proof of this theorem. What's much better is to learn how to apply this theorem. And so the way that I would practice applying this theorem is I would go back and verify that something like NZ is actually a subring of the integers. And another thing you could do is you could check that the Gaussian integers, Z adjoined I, is a subring of the complex numbers. Each of those would be good things to do to test your applications of this theorem instead of really spending your time focusing on the proof of this theorem. Now, the last thing that I really want to discuss in terms of rings are some properties of rings. Now, what I would say is that rings have very interesting properties, but what I would really caution, or what I should say to you, is that rings sometimes behave badly. Or I said way at the beginning of these videos that the integers are a very good example of a ring. What they really are is an example of a ring that behaves quite nicely. And so some of the properties that you are used to with respect to the integers do not hold for general rings. And so you have to be careful with these inside notions and these ideas that are really ingrained in your head about universal truths. They may be universal truths about the integers, but not of all arbitrary rings. So for example, what I mean is cancellation is something that does not hold in general in an arbitrary ring. That is, there's this particular fact we're really used to about the integers. If I start with a non-zero number a, and I'm looking at the equation AB is equal to AC, we're very used to canceling the a's, so to speak, and concluding that B is equal to C, but this is just not true in general in an arbitrary ring. In an arbitrary ring, we can start with a non-zero a, have an equation AB equals AC, and it may not be true that B is equal to C. So you're not allowed to cancel things off of the left or the right hand side of an equation when you're doing computations in rings. The next badly behaving property of some rings is that the zero product property does not hold in rings. So if you remember what that zero product property says, it says if you're working with integers and you take 2 integers and multiply them together and this results in the number 0, then either A is 0 or B is 0. That's true of the integers, but that is not true in an arbitrary ring. So for example, there are rings out there in which you can take non-zero elements A and non-zero element B, you can multiply them together and you can get 0. And the last property of rings that we're very used to with the integers or with the real numbers, but which is not true in an arbitrary ring, is that linear equations can have more than one solution in an arbitrary ring. So for instance, if we were looking at an equation ax is equal to b, this is really like the equation of a line, right? We're used to there being either 1 or 0 solutions for the possibilities for x. However, if you're looking at this equation ax equals b, where a and b belong to just an arbitrary ring, and x is serving as a sort of indeterminate, there might be 7 solutions to this equation. There might be 10, there might be 4. And so really you have to get that notion of, oh, there's at most one solution to this out of your head if you're working with an arbitrary ring. And I've said that these properties, rings can behave badly, and I haven't given you an example because what I'd really like for you to do is, as an exercise, find an example of a ring where each of these bad behaviors does take place. So find an example of a ring where the zero product property does not hold. Find an example of a ring where cancellation does not hold. Find an example of a ring where you have a linear equation and you have many solutions to that linear equation, more than one. Now, that concludes our introduction to rings, but I'd just like to put a summary up here of the things that you should have gotten out of these videos or from reading your textbook or looking at some further examples. So the first thing I want you to be able to do is I really think you should understand and know by heart the definitions of a ring, subring, and the Subring test. The next thing that I hope that you'd be able to do is that you'd be familiar with examples of rings, and not just the common examples like, oh, the integers are a ring, which is true, but it might not be the most representative example. It would be great if you could, at the top of your head, have some examples of rings that don't contain a unity and some examples of rings that are non-commutative, and then start piecing together some combinations of these. Can you come up with an example of a non-commutative ring that does not have a unity, for instance, which is something that I didn't cover in here. And last but not least, I'd like you to be able to work with examples of rings where familiar properties like cancellation and the zero product property do not hold. So be able to come up with examples of rings where that doesn't work, but still be able to solve, right? So if I give you something like, suppose 5b is equal to 5c in some particular ring, find all different possibilities for b and c, you should still be able to do that without trying to cancel the 5 away.